In just previous lecture, we have learned the random forest, and the advantage of this random forest is that it automatically reduces the variances. Okay, we have learned this thing, random forest, in just previous lectures, and its main advantage is it is reduced the variances models. And the random forest is the most famous ensembles model that used the bagging technique. Okay, so random forest, the advantage is it's reduce the variances. It's reduce the variances. Okay, and why? And also we have to know that the random forest models is also a low bias model, because why? Because random forest, because the base learners of the random forest, that is the decision trees, are low bias. Because of that, random forest is a low bias models. Because our base learners here, sorry, I think I have mistake something. It will be base learners, NERS. Base learners, MIs, are low bias. Because only of these regions, it's a low bias model. Okay, and also it reduces the variances. It also reduces the variances, because why? Because if you just remember, the random forest is in some one kind of ensembles models that we have to build the random forest. We have used the bagging technique. So to build, suppose let's take M is our random forest. M is our M ensembles models, that we have to build the aggregate the base models that we built by simple using the aggregate of the base models. So let's take, we have base models M1, M2, M3. Suppose let's take up to K, we have base models, and we have built these ensembles models by using simple aggregate, taking the aggregate. Now the question is that how to choose this proper K. This is the main questions, how to choose this proper K. So to choose this proper K, then first we have to understand what is the importance K here. So suppose if we increase the value of K, means what? If we increase the value of K, this means our number of base learners is increased. This means what? This means number of AMIs is increased. If number of AMI is increased, then then we have to increase the sampling of our parent data, of our training data. We have to increase the sampling. If we increase the sampling, then every sampling, the number of points for the every sampling is reduced. Because of that, we have reduces the variances for age based models. We have reduced the variances for age models because of that. And the opposite is also, if we decrease the value of K, the same things here, the number of base learners is also decreased. That implies that we have increases the variance. Okay, this is the simple relations of the variances and the number of base learners. Now if you just see this thing in practically, actually our base learners, just we are using the some small number of points from our training data to use to build the base learners, that is small samples of the data from our main data. So because of that, in our base learners, our bias is originally low, and the low bias and the combinations of and the aggregations of the low bias models also produce a low bias models. Okay, because of that that reasons we can and conclude that our bias of our ensemble models is same as is approximate, not equals to same, is approximate equals to bias of our age based models, that is AMI, approximate equal. And typically the k value typically the k value is taken near about typically this k value is taken near about 2500. Typically that's depend on the situations, what is your actual problem and what kind of data you have, that's depend on our to choose. Now the question is how to choose the sample. That also in previous series of lectures we have seen by sample using cross validations, k-fold cross validations, features forward selections. So such kind of technique they are already have to choose the best k. So that the same things also is applicable here, but the same thing is applicable into a small chunk of sample data. The same things also applicable here. So suppose let's take suppose for our sample set, let's take we have a data set dn. In this data set, suppose let's take we have d features and n number of data points in these data sets, and now we are sampling from this data set. We have produced the sampling data d dash from this data set, and in this d dash data sets we have d dashed number of columns and m number of data sets in these data sets. And how we'll produce it, we have taken the random row sampling here and column sampling here. This simple, just doing these things, row sampling and sample, and obviously this d dash is less than is equals to d, and also this m is also less than is equals to number of n. So it is obvious things. So now the questions is here also. Here actually we have seen here one parameter k, but here also we have two parameters. So let's see what is these two parameters. So the two parameters is the column sampling rate. That is simple. The d dash by t, and a row sampling rate. This is simple, m by n. Okay, and these two are also to another hyperparameter. Now the questions is the reduce we have, if we reduce these two sampling rates, then our sample data will also be small. Just simple, if we reduce this column sampling rate, means what, we are reduce the value of d dash. Similarly, we also reduce the value of m. Because of that, we have reduced the column sampling rate as well as the row sampling rate. If we reduce the d dash and m, this means the sample data site is reduced. So because of that, if we reduce the column sampling rate, means what? Means we are build a low bias models. That we also see. If we taken the low sample data set, small sample data sets for age based learners, that means we have taken the depth of the age decision tree. Is correctly, we have taken we have consider all the data points from these small samples of data. Because of that, we are reduced the variances for age decision tree, for age based learners here. Because of that, we have reduces the variances. If we reduces these two things, means that we are building a low variance model. We are building a low variance model. Means what? We are decreasing the variances for S model. This is simple. So here we have seen, actually here we have a three kind of parameter. We have a parameters, three parameters. We have three parameters. First one is K, second one is column sampling ratio, and third one is row sampling ratio. These are the three parameters. And the K means K is responsible for the number of base learners. This is simple. The how much we have to choose the column. Number of depends number of D test, and D depends number of M. now the one thing, how to just we have just till now we are using the D training. Now also we have from the whole data. Suppose I think it will be understandable if we draw this thing algorithmically. Flowchart. Just draw the flowchart. Suppose let's take we have the DN data sets. We have the suppose it's the sample our train data. This is the train data. Also for this is the train data, that from this train data we had only sampling. This is from this train data we have only using the sampling technique. Suppose let's take this sample 1, sample 2 by this simple row sampling and column sampling we are doing or build the S sample. And according to the S samples we build our base learners models. And for similarly for years, for similarly for, and after that we are building our N sample models by simply aggregating the S models, by sampling aggregating the S models. So this is our N sample models that actually we have seen. But till now this is simple or train data, but till now also we have the cross validation data. And also we have the test data. Also we have the test data. So we have using these two datas by sample find this cross validation data we have used to sample find the best K. So we use these to find the optimal K, means best K, means number of base learners, and D test and D test data, that data we are using to report our models, how much accuracy our build, our ensembles models to build the report of the model. To build the report of the models, that's data we are using. Okay. Now just see these things. Now see this. Now see these things. So one of previous lectures we have seen that, and we have seen that how these cross validations actually work. So suppose let's take this is the performance that is the K. These axes that denoted the K. Suppose 1, 2, 3, 4, and according to that K, we have sample increase the value of K, and corresponding we are performing the performance. We are calculating its performance from this data set. From this data set, we are calculating its performance, and from this data set, sample, and from this data set, we have considered the value of K. Suppose let's take, and if we consider the value of K, our performance is suppose here. If just after taken our performance is here, after increase the performance here, after increase the performance here. So you will see if we increase the value of the K, our performance is increased, and after some time we will see that after some time it will be constant. It will be constant like that plot. in a typical time, in typically we will see this kind of, if our data sets, all our given data sets is poppers and everything is and in our data set everything is means our data sets is equally sampled, and they are have no equal, everything is okay. If everything is in right direction, so then we will see this kind of plot we are drawing. And in this plot we have to decided that our best k will be here, because our best k will be like here, will be like here anywhere. Suppose let's take its value is, suppose let's take its value is k dash, suppose let's take its value is k dash. After that, if we increase the, if we just in building the model after increasing them, but we'll see that our performance is not so much increased. Okay, so because of that, because suppose here, suppose let's take our k is equals to 200, suppose let's take here our performance k is equals to, suppose let's take 2000. We have to train our models on this huge we have to use this time. Okay, and we have to also use our resources to build it, but we have seen that our performance is increased not so much. But here in these regions we have dramatically increased our performance. But in such regions, but in just see these regions, but in these regions our performance is so much increased. So we have to consider, so in such scenario we have to consider this k dash. This k dash is our best k. This k dash is our best k or optimal k. So I think you will understand the thing, how this bias and variance here actually occurs in the ensembles models. So a simple random forest, you will see that there have three kinds of parameters, that is k, that is number of base learners, and column sampling rate, and the row sampling rates. In typically the industry we will see that, we have seen that actually we have seen that this ratio typically they have using for column. Suppose let's take we have using the row sampling ratio or 20%, and column sampling ratio, suppose let's take we are using here 50% column sampling ratio. Okay, and we have to choose a such limit that our data set is not so small that it is so small that our models is nothing have to train in our models. So we have to take a general typical rule we have to use, that our data is not so small, our sample data means our sample data is not so small, as well it's not so big to build bias models. Okay, so such kind of thing we have to mind to build this thing. Okay, so I think you will understand the main motto of this bias and variance trade-off, how to choose the right parameters by sampling these. So these things are depend on ourselves, column sampling ratio and row sampling ratio. It is the general rule. In our general line we have to choose such a value that our sample data is not so small or not so large. So we have to to build a ensembles model, we have to mind this thing first. And the second thing is to choose the right k. We have using here the cross validations data sets as usual. Okay, these three things we have to mind in to build a ensembles model. I think from these lectures you will clear you got some concept about the bias variance trade-off, how these things actually internally work.